Well, I thought I would join in with Janet, architect of the architect of ideas, and I got a cup of. I was going to have a cup of tea, but I decided I needed a cup of coffee, so I got a cup of coffee. And I thought maybe if I try not sitting at my desk away from the computer and using paper, that it might be completely different. So here I am. And that's what I drew while I was listening to her reading that first part of Measurement. And I didn't find the link to the PDF, and I didn't search for one. So I did look for it on Google, and I found another thing voiced over by some paid actor or something. Wasn't as nice to listen to, but I did manage to listen to a little bit more of it, and it was really interesting that he goes on to talk about measurement without deciding on the units in advance. But even before I did that, I drew these diagrams because what I was thinking was about the converse of that theorem, that if you join the points of a triangle to the midpoint of the opposite side, that they all meet. The converse is not true, but it's fun to think about what is true about the other way. If the lines joining the points to the opposite sides all meet at a point, then what can you say about the places where they divide the opposite side? And I started out by just drawing, without deciding which triangle it was. I started out by just drawing these three dividing lines and then choosing points on each of them and making a triangle out of those points. And when you do it here, you get this kind of thing. So this one is kind of halfway. But these two aren't. And so then I did it just with the one where it is halfway. And then I did it with an equilateral triangle where it is halfway. And then I thought, well, these things kind of can be repeat all over the page. So so I drew a hexagon, and you can see that you could put another hexagon here and another hexagon here. It would go up to there. So you could have this pattern repeating all over the plane. And the reason that I did that was I was thinking about what happens when you take an equilateral triangle, which does have this property, a bit like that one, and if you deform it by mapping it to another triangle, like that or like that, this map is going to map straight lines to straight lines. And so this map will constrain the movement of the points as you move it. And then I realized that you can also look at this thing as a three-dimensional shape. So that these are let's say that's the x-axis, and that's the y-axis, and that's the z-axis vertically up out of the, you can think of the x and y as being in the page and the z as being vertically out of the page. And then this is a projection onto the page of that other one. And I thought that would be a way of defining the map. So in the dimension above, you can get I don't know if you can get all triangles by rotating, by looking at an equilateral triangle at an angle. Can you get every other triangle? It kind of seems like it might be possible. So I actually, from other maths, I kind of know that there are these. This is how, when I was a kid, how I learned to write computer programs which draw three-dimensional graphics. What you do is you map. You have three-dimensional graphics, three-dimensional coordinates in your computer, and then you do the projection. You calculate what the two-dimensional coordinates are when you project them onto a page from a particular point of view. And all you do is you just take your eye in three-dimensional coordinates is looking at something in the scene, in the three-dimensional world, and you imagine a piece of paper that's kind of between you and what you're looking at, and your eye, there's a line through that piece of paper towards the origin of the three-dimensional world in your computer that's represented by these coordinates x, y, z for all the corners. And all you do is to get it to go to 2 dimensions is you, for each point in your scene, there's a line from your eye to the point which cuts the page at a certain place. And so you you can calculate those places with trigonometry, and you just calculate the points of intersection, and then that's your 2-dimensional picture. So you can use that process in reverse to say, where would I have to put the page in this scene in order to make the triangle project like that onto the page? And it's kind of down here somewhere, because if you imagine this is an equilateral triangle, then this is the point nearest you and that's further away. So it's a projection of an equilateral triangle lying like that. And likewise, that's a projection of an equilateral triangle that's just tilted in, where this one, because this is on the midpoint, so all the symmetry arguments work for this thing, but they don't work for that because it's tilted down. And no, they do work for that because I started out with them working for that. And the other thing about that projective picture is you can make the triangle bigger or smaller by moving your by moving the paper nearer your eye. If you move the paper nearer your eye, then the projected image gets larger. No, it gets smaller. And if you move the paper down away from you, the projected image gets larger. So you can squish the triangles. You can make them bigger or smaller, and you can kind of deform them. So that's what I thought. And I suppose I should try and think something else, because that was all what I did before I sat down here. What else can you do just to understand this? Oh yeah, I know. I don't know. But it was interesting that comment she made about analysis, that you suppose something is true and then follow the consequences of it. Because that's not actually what the way I thought of analysis as somehow some kind of process of splitting or dividing things up. So I've been misusing the word. I need to find another word then. The thing is, I did these drawings sitting at my desk, and if I do these drawings slouching on the couch like I am now, then I don't think I'll do such good drawings, especially if I've got to hold the phone in one hand. So maybe I'll end it there. And Janet did another video on the 11th of November 2023, reading A Mathematician's Lament, and there was some kind of demonstration outside the house by the sounds of it. I didn't have demonstrations outside the house, but I had them in my head. In November 2023. And now I've got things like ideas like cultural identity in my head. Although I don't have much of an idea of what that is. So, but I did notice that this way of dividing up a grid and putting patterns on it and then choosing certain lines is the basis for a lot of Islamic patterns. And there's some really nice explanations of how you can do these symmetrical tilings by repeating this and then choosing certain things to leave out, so you can get a star or you can get crossed over things, and you can put pentagons in here and hexagons out here, and you can then join them up in certain ways and generate patterns. And these transformations between one representation of the plane and another, there are something like 17. There's a theorem which shows that there are only 17 ways there's 17 groups, symmetry groups in 2 dimensions, and they do things like rotate or reflect or translate and reflect, which is called glide symmetry or something, or glide reflection. And I remember proving that there were just 17 of these things. And apparently all of them are in the Alhambra in Spain. You can find these types of designs on carvings and on the walls, and all 17 are represented in there somewhere. But it is very interesting to look at how the Greeks and the Arabs developed mathematics kind of separately, but it's very hard when you look at Euclidean geometry and these Arabic patterns. They look like 2 different cultures, but there's mathematics that will join them together. So I think that's kind of an answer for Vanessa Beeley, because I asked her, we were talking about what Arab identity is on her Patreon, and I said, because I don't know what any cultural identity is. So maybe that's a help.